Okay, so we're going to continue on in chapter 1, which is the first part of our module 1. So I'm going to go into module 1, part 1, learning plan. And I'm going to pull up the PowerPoint presentation that we had started last time for chapter 1. I'm going to zoom out here just a little bit. Oops, I guess I can't. And I'm going to catch us up to where we had left off the last time. So we talked about terminology, and then most specifically, we were talking about and getting used to the standard symbols and how to represent mechanisms using the kinematic diagram method. So we had done 2 kinematic diagrams. We sketched this particular shear. And then we also on AutoCAD, we created the kinematic diagram for this vice script. So we are ready to then move to our next slide here in the PowerPoint presentation, which we're going to go to section 1.7 called mobility in our chapter. So if you want to open up, this is going to be found on page 8 in your book. Okay, but I have the information here. Okay. So, so mobility, another way to describe mobility is, and you may have heard this before in regard to designs, is when we look at degrees of freedom, or we're trying to decide how many degrees of freedom are there on a mechanism. And so what it refers to is the number of independent inputs that are required to precisely position all of the links in the mechanism with respect to the ground or the frame. So what I like to think of is it tells me how many things I have to do in order to complete the operation or the function for that mechanism. So do I have to do one thing where I just rotate something around? Or do I have to do multiple things, maybe move a bunch of handles and things in order to get it into its proper final position? So degrees of freedom is really important because we want to, know up front, like what we're up against. So each one of our mechanisms, as we put our labels on both the number of the link and then also the letter of the joint, we have to be complete with that because then we're going to be calculating the degrees of freedom in a quite simple equation, not going to be hard to do, but it's one of the first steps that we always do before we continue on with going to the next steps with kinematic analysis. So we are going to use what's called Grubler's equation. Now there's 2 different, well, we'll just use F. I'm just going to adopt F. In previous chapter or in previous editions of this book, and also in my previous life when I was doing kinematics, we always used we used the word mobility to calculate the degrees of freedom. So we usually said M is equal to. This book uses F, I think, for just freedom, degrees of freedom, maybe. Bless you. And so we're going to say that our variable for mobility is going to be F, which is degrees of freedom, is going to be equal to, and it's going to be 3 times n minus 1, where that n, you can see here, that lowercase n is going to be equal to the number of links in the mechanism. Okay, that's why we number them in our diagram. All right, so whatever our highest number is, that's going to be the number of links in our mechanism. So it's going to be 3 times n minus 1, and then minus 2 times JP. JP means a primary joint. Pins and sliding joints are primary joints, okay? And then it says minus JH. Those are higher order joints. The 2 higher order joints that they most often reference is going to be a gear and a cam. But as I had stated earlier, when we talked about these different types of joints and how to represent them in a kinematic diagram, I let you know that we will discuss and go further with gears and cams when we specifically have them as a module a little bit later in our class. So we won't be dealing with JHs, so no higher orders here. So we won't be doing mechanisms that involve gears or cams. We're only going to do primary joints. So pins and sliders are going to be what we're going to deal with. So we can really take this equation and just truncate off that JH because we simply don't need it. And our equation can then simplify, if you would, to 3 times n minus 1 minus 2 times JP, okay? Now, Our number of degrees of freedom, as I told you earlier, is how many inputs are required in order to get our mechanism to accomplish the task that it's meant to do. So, so for instance, if I only have 1 degree of freedom, that means I only have to do one thing. I maybe have to, we saw a toggle clamp the other day. I maybe just have to move that handle on the toggle clamp. That's one operation, 1 degree of freedom in order to get it to clamp or unclamp. Okay. We had looked at that vice grips that we had the other day. We kind of held it on one handle and then we let the rest of it kind of, you know, dangle down below. But while keeping the one handle in place, I really just had to move the other handle 1 degree of freedom in order to get that jaw to open and close on the front end. Okay. So when there's 1 degree of freedom, first of all, it's very easy to use. There's only one thing to do to get it to do what it's supposed to do. It's not complicated. So it's desirable to have 1 degree of freedom. But it's specifically called a constrained mechanism. Okay, constrained mechanism. Now, if there's 0 degrees of freedom, that means that it's locked. Okay, that means it's not going to move. And really, it represents a support or some sort of a frame. So like a truss can be considered a constrained or a locked mechanism because there is nothing that we can move to make it move. And really by function, we don't want it to move. We want it to support. And then the last type is unconstrained. And this is when we have more than 2 degree or more than 1 degree of freedom. We have 2 or more, meaning we have to do multiple things in order for us to get our mechanism to do its final task that we're intended to do. So, so we will see an example of that. Okay. But most often, and predominantly the majority of what we study in this class, because it's the one that's continually reapplied in kinematics, is going to be the 1 degree of freedom, the constrained mechanism. Okay. So let's look at an example, and we are going to do, if you would, a full problem. Now, this again is going to be one of the practice problems that you're going to be handing in. So you're going to want to follow along here. So if we go on the top of page 9, so I'm going to go underneath our book and we'll look at the problem statement itself. Let's zoom in here. Okay. So we have this toggle clamp. Oopsie. We have this toggle clamp. Try to focus that. There we go. And it says we want to draw the kinematic diagram for this toggle clamp. And we also want to compute the degrees of freedom. Okay. We want to find out how many things do we need to do in order to get this to clamp or unclamp. Okay. So, so first things first, we need to draw the kinematic diagram. Now, what I want you to do before we cross over and we look at AutoCAD, which we will put this on AutoCAD, I want you to have another example of how to do that. But I want you to sketch what you believe the kinematic diagram could look like for this mechanism. So take a moment, grab a piece of paper out and sketch the kinematic diagram for this toggle clamp. And if you're not exactly sure, that's okay. That's why we're actually doing this. Okay. I want to make sure that before we start translating this to CAD, that we understand and we know why we're doing what we're doing. So just take a moment to just sketch out what you think it should look like. Now, when we create a kinematic diagram, it is not complete until we have all of the labels on there. So you need to label each one of the links. You need to label each one of the joints. Okay. So make sure you include that in your sketch. Okay, the sketch that I came up with looks like this. Okay, it looks like this. So remember, a kinematic diagram is always going to be a simplified version of whatever our mechanism is. Okay, so it's just representing. So we're not putting, details in there like thickness or even, sometimes how the part looks. We have something very, very stripped down and simplified. So as we do our kinematic diagram, I'm just going to kind of walk through the process of what I thought about as I was doing it. So first things first, you always have to identify what is the frame. Okay, the frame is going to be anything that is not moving. Okay, so as we look at the toggle clamp itself, it's kind of obvious that these little L brackets on either side and they have holes in them, that's going to mount down on something in order to keep that, in place. So these L brackets on either side where the rivets are going through, acting as pins, primary joints, these two pins are not going to move. So those two connections are going to be connected to the frame. So you will notice that those two connections right here, I represented with the standard frame symbol. Okay, standard frame symbol. And by identifying it as the frame, this is going to be link number 1, not a joint. It's a link number 1. Even though it's not moving, it still is part of the mechanism. And remember, even though it's two separate connections, in this case, it is the same part, but it can be physically different parts. It just means that that part is not moving. That point is not moving. That connection to the mechanism is not moving. And all of it, whether it's two separate pieces or not, physically two separate pieces, it's still considered just one link, which is the frame. Okay. Then you're going to notice that the next thing that I did was I started looking at, okay, what's connected here. So there is a link that goes from the right side connection to the frame up to the right pin on our handle. Okay. So I represented that by a very, simple method. Notice that I've got the pin connection with a circle that is filled in at the center of our frame symbol. And then I have that same filled in circle at the joint or the pin where it's connected to the handle. Okay. It's just a straight piece, a straight link. So it's just a straight line connecting those 2 points. Okay. This would be link number 2. Okay. Now after link number 1, as I stated the last time we were together, the numbers of the links become arbitrary. You do need to use 2 as your next link, 3, 4, however many links that there are, but do they have to be on the same ones that I'm identifying? No, not necessarily. But you're going to find that as we kind of move along, it's going to start to become kind of standardized why you do what. I usually start on what I call the input side of my link. So here's my handle. This is the input side. So whatever comes from the frame, the first thing that's in that order, if you would, I always call that my next link, number 2. Which means that number 2 is connected to the handle, which is number 3. Okay. Notice that each one of these numbers has a circle around it. I will be looking for that. And when we set up our start file and that kinematic start file, we put the circles around each one of the link numbers. So make sure you do that. Don't just put a number out there without a circle. Now, the other thing that I added on the end of the handle was this letter X. This is called a point of interest. because that handle is extended out and we're going to manually be, operating that, it's always good to kind of know like where that point is in space, how far away is that? What's the rotation going to be that's going to be expected? And then once you analyze it through, its full cycle, is it reasonable? So identifying a point of interest when it seems to make sense is a good idea. All right, so that's our third link. So now the third link is connected to what would be kind of that clamping portion in the front. Now, this can be represented a lot of different ways. And from the designer's perspective is how you're going to take it. Meaning you would know if I'm designing this, I would know more about the environment that this is in. Meaning, is there anything that I need to be aware of that it could interfere with? That I'm going to want to make sure that I represent that as part of that link. Okay. So, so what I did was I felt, here's our connection to the frame. And then there's the points to our connection with the handle. So that's just this line right here. Okay. But then it has the other stuff out front. So why did I choose the shape I did? I felt where the clamp is, where it's actually physically going to, push down on an item. I want to know where that is. Okay. When I'm designing. The other thing that I want to know is how high this is, because I want to make sure as it rotates, up and back, that it's not hitting, something else. So that's why I chose the shape that I did. Now in the book, you're going to notice that they use a lot of like just triangles. Okay. Well, that's their choice. You can change it up, but not adding all those details. So it still doesn't look like the front of my clamp, but it kind of covers the extents of what I feel would be the parts of it that I would want to design for. Does that make sense to everybody? Or to consider as I'm laying this out and showing what it's going to do through its full movement. Okay. All right. Now I would call this link number 4. So I'm going to put a circle around that. So now I have all my links identified. There's 4 of them. The next thing is to identify each one of my joints. So again, I always start kind of at the beginning where I chose to have my first links connected to the frame. So I would call this joint A, my next joint B, then C, and D. Now I also want to make another point here is that you will notice that the only place that I have letters, I have the joint symbol, which is the circle filled in, is where there's a physical connection with a pin going through it on this mechanism. So if I look here, there's 1, 2, 3, 4 pins. Do not put a joint at the endpoints of each part of a link that you draw, only where there is a connection. Okay. So notice I don't have a pin joint at point X here, because that's just the extents to the end of the handle. Oh, and what I didn't do, and I'm realizing that here, I would probably call one of these or both of these another point of interest. So if you wanted to label the points out there, that's fine. So I've got A, B, C, and D as my joints, my pin joints, and I've got 1, always the frame. You cannot call anything else number 1, just so you know. All right. So if you're like, well, she said it was arbitrary. No, I didn't, not fully. Number 1 is always the frame. 2, 3, and 4, as we move into each one of the links, those you can, maneuver around a little bit and it won't be wrong. Okay. But number 1 is always the frame. So calling out those 4 there. So any questions as we look at the sketch that we have here for our kinematic diagram? Okay. So then what I want to do, the next thing is let's go to the AutoCAD and make sure that we can create this diagram over there. So as I said earlier, I already have pulled up AutoCAD and I've got my kinematic start file here. First thing, before I do anything else, because I don't want to save over the top of this, I am going to go and I'm going to say File, Save As, and I'm going to call this example 1_3. So example 1_3. Enter. Okay. So now up here, I'm just going to double check. It changed the name of this file. Okay. Because I want it to be there. So now what I have the freedom to do is to move these around and represent the kinematic diagram that I just created. Okay. So I have one, I'm going to move this. So I have one frame member. I'm going to copy and I'm going to create the other frame member. Now, when I'm doing this, I just want you to know that I'm demonstrating this so that you can kind of, know what's expected and what to do. I am not here because you guys have already had AutoCAD. You should be familiar enough to kind of, maneuver things on your own and know how to copy and move and such. If you need help during our open lab time, I'm happy to come around individually, but I'm not going to stop and make sure everybody is all set here in the demonstrations, just so that you know. And then the next thing I'm going to do is I'm going to change this to my object line layer. And I am going to create a line. I'm going to start at the center here. And I got to turn my ortho off. And I'm going to represent the first link, which is number 2. And then I'm going to add, copy over my joint. And center here to the endpoints. Okay. Now on the end of there, I am going to add the representation of my handle. And I think I go over here-ish. And again, remember, we're not given any dimensions here. So we're just drawing things right now proportional. And then I'm going to go back to the beginning here. Okay. And then I'm going to copy again that joint from the center here to the endpoint there. So that's my handle. I'll add my labels after I have everything in place. Now I'm going to go a line from the center here to the center there. And then now I'm going to draw that front end of the clamping link. So I kind of put it here, here, and something like that. Okay. All right. So in this particular kinematic diagram, there is not a sliding element. So we can just erase that slider. And I'm also going to erase, I'm now done with my, my joint. And then what I'm going to do is I'm going to move over the labels for each one of my links. So I'm going to move number 1 from here to here. I'm going to move number 2 from there to there. I'm going to move number 3 from here to there. And then number 4 is going to be this element here. Okay. Now, again, the number with the circle is identifying each one of my links. Okay. Now I'm going to move my A, B, C's, and D's. Now, the other point I want to make here is if you have a kinematic diagram where you have more links, then you are going to add more. We're not just restricted to 4 here. 4 is going to be the one that we do the majority of the time. It's called, we're going to find out, a 4-bar mechanism. But if you do have more links, then you just continue to add them. Now I'm going to put my joints in place. So I'm going to move A to there, move B here, move C, and I'm going to move D. So those are the labels for each one of my primary joints. And then lastly, I'm going to move X to the end of our handle, and I'm going to move Y to the clamping point. You could have a Z, I guess, if you wanted to up in the top here, but probably the clamping and the handle means the most to me. All right. And then you want to make sure that you have a way of calling this out. So I'm just going to add multi line text here, and I'm gonna say example 1.3 kinematic diagram, right? Or we don't even have to write that. There we go. Oops, I'm gonna put this on the notes layer to make it official. So let me put it there. There we go. Okay, now for your practice problems, then you are going to add to the document that you started the last time we were together. Okay, so we created the document for your practice problems for module 1A, and that had our first screenshot from the vice grip's kinematic diagram. Making sure that you label, okay? If you don't label it here, then on the actual piece of paper or the document where you put these on, I need to see it labeled. I'm not going to try to figure out which example is the drawing that you did. So make sure you label these with the example and that I can see everything. If you have a dark background and you use dark colors and I can't clearly see what the values are, you're not going to get points. So picking something like pink or yellow for the call out of the numbers and the letters is good. If I do something like a dark blue, it doesn't show up. It's very hard for me to see. And I'm simply gonna, that's part of readability. Okay. So look at your files before you send them over and make sure that I can read them and that they're nice and clear. Okay. You guys are in your second year of the program and we're preparing you to be professional. So if you were going to be showing this to your boss, okay, you want to be sure that they can get the information that they need. So use those eyes as you're submitting your homework, okay? And then now I would take a screenshot. So on my computer, it's the Windows Shift S, but I know that there's other ways that you can get a screenshot. And then I'm just going to select that area. And then now it's on my clipboard and I can then pull up that document and drop this in. I don't know if I saved mine from yesterday or not. If I did, I'll pull it up in there. I forget if I did. Oh, I think I did. Look at that. Okay, great. So this was my first one. Now what I'm going to do is I'm going to just hit enter and go down, and I'm going to say Control V. And now there's my kinematic diagram for example 1.3. Okay. So you notice that I have the label here. If you forgot to put it in your screenshot, then just identify it here on the document. You could put a line in between here and say example 1.3. Okay. And then you're good to go. Does that make sense to everybody? So, so just making sure that I know what's what. Now we're not done with this problem. That's just the kinematic diagram for this one. Okay. There's a second part to this. You have to calculate the mobility. So we're going to use that Grubler's equation and we're going to then calculate the degrees of freedom for this mechanism and see what we get. Okay. So I am going to go back underneath. And now how you submit this for the practice problem and or the assignment, because you're gonna have to do these for the assignments as well. There are a couple ways that you can do it, okay? You could have a sheet of paper like this and neatly hand draw your calculation for me. That would be one way. And then you would submit this as part of your practice problems, okay? The other thing that you could do is in AutoCAD, you could in text add the information that we're gonna write down right now. So you could put it as part of your screenshot. Okay, so so either one of those, as long as I know what the calculations are for, what example, what assignment number they're for, you can hand it in that way. So I am going to, right below the kinematic diagram that I sketched earlier, I'm going to use Grubler's equation now. Now, when you submit anything that has to do with equations or math, you have to always show your work. So many of you have had me for statics. So you remember, we always want to first show our equation in variable form. So you're going to tell me what you're going to do before you do it. Don't just start randomly putting numbers down, because guess what? That'll be a 0. Okay, that'll be 0. You won't get the 5 points for the mobility calculations. Okay, so my equation is going to be F is equal to, and if you need to go back to the PowerPoint, I'll show you where it's at. It's just right up here. F is equal to 3 times N minus 1 minus 2JP. And I'm going to leave off the minus JH because we don't have any higher order joints. Okay. So it's going to be equal to 3 times N minus 1 minus 2JP. Okay. Now, N is equal to the number of links. And JP is equal to the number of primary joints. Okay. I'm just putting this here for you so you know what each one of those variables means. You don't have to write that out. But you do have to write out F is equal to 3 times N minus 1 minus 2JP in a way that I can read it and understand it. Okay. Then directly below this, you're going to write in the numbers. Okay. So this is showing your work. 3 times now N, the number of links. I look up here and I look, okay, what was the highest number link that I identified? It was number 4. So the frame is always included in the number of links. It just happens to be a link that doesn't move. Okay. So 4 is going to go in here minus 1. It's the equation minus 2 times the primary joints. So my primary joints are the pins, all the pins in this case. So any letters that you have. So there's A, B, C, and D. That's 4 primary joints. So that's going to be 4 right there. Okay. So now we're going to do that math. So if I take in the parentheses here, 4 minus 1, that's going to be 3, right? 3 times 3 is 9. 9 minus 2 times 4 is 8. My mobility for this problem is 1. You're going to put a box around your final answer. Tells me that you're done. This is the mobility value for this problem. Okay. So you need to write your equation in variable form. This equation right here, just as you see it. Then you're going to show your values from your diagram above. So you're going to put in how many links there were, how many joints there were. And then you're going to do the math and you're going to give me your final answer. Show your work. You're going to do this for each time that you have a mobility equation to do. Because part of the process is, number 1, create your diagram, and number 2, calculate your degrees of freedom. It verifies or certifies, if you would, what your diagram looks like. Because if you get here and you're like, well, I know there's only 1 degree of freedom, one thing that I have to do to make this clamp do what it's supposed to do, which is move that handle, and I get a number other than 1 for my mobility, then I might be missing something up here in my diagram. I might not have enough joints identified, or I might not have my links appropriate. Okay. So it verifies that everything is good above. So you'll know, as you look at a diagram, oh, the mobility is going to be 1, but now this proves it. And it makes sure that you have the right number of links and the right number of joints identified in your kinematic diagram. Okay. All right. So then this, I would take a picture of, and then I would submit this. Now you can continue all on one sheet if you want to show the mobility for each one separately. Like this is, for example, 1.3, you're going to show that equation. Then directly before, you're going to go example 1. Whatever our next one is that we're going to do, and so on, and just show the mobility equations on one sheet of paper. Totally fine, as long as I know which mobility equations go with which examples. Okay. You're probably also going to ask, do we have to hand in the sketch that we did? No, you don't have to, but if you have it there and then you have your mobility equation right below it, just include it, right? I probably would just include it, but it's not a requirement. I'm really more interested in the CAD one because that's what you're going to use going forward. You're always going to draw things to scale using AutoCAD. So I want you to get that practice. Okay, so any questions about example 1.3? No? All right, let's do another one. So we're going to turn the page. And the next example we're going to look at is going to be a can crusher. Okay, so let me go back to my PowerPoint and just catch us up. We did example 1.3. We're going to do example 1.4. Okay, and we are going to, if we look at this example in our book, it says this is a figure of a beverage can crusher used to reduce the size of cans for easier storage prior to recycling. Draw the kinematic diagram using the end of the handle as a point of interest. Also compute the degrees of freedom for the device. Okay, so we're gonna do that very same process that we did last time, but this time you'll notice that the can crusher part that's gonna actually crush down, this is gonna be a slider. It moves linearly. So instead of just the pin connections like we had in our last one, we're gonna be representing a slider for this one. So we'll get to, see how we would do that in CAD. So first things first, we're going to draw this kinematic diagram. I want you to make a sketch of it first. Okay, so go ahead on a separate piece of paper, sketch what you believe the diagram should look like. As we look at it, just as a frame of reference, we're going to be looking at a side view. This is showing kind of a perspective and isometric. We don't draw kinematic diagrams like that. We're going to go straight on right here. And you'll notice that here's the handle. And then this L bracket right here, that would be the frame. That's the part of the mechanism that's not moving. So anything connected to that frame is going to then be identified as such. Okay. Now, if you wanted to, they do have a representation of the kinematic diagram further down on the page. So, so feel free to peek, but see what you can do just by yourself and, using what we've already learned. So as you're looking at this, as you know, first step is always going to be identify your frame. So what is the parts or the connections that are not going to be moving, okay? And the handle right here, that's going to be a frame member for you, okay? So you'll use that as one of those symbols. Okay, let's start going over it together. So, so what I'm going to do is I'm going to kind of try to get this up here so we can maybe see both at the same time. Let me get it on here. Maybe I will. There we go. So I'm going to start by using that point where the handle connects to that like L bracket. That is going to be my frame member. So I'm going to draw that in place. Okay. That means it's not going to move. Then I'm going to draw my handle. My handle is the thing that's connected to it. And it's also considered the input. Okay. Now, as I look at this can crusher, and I look at that angle, you'll notice that I am going to show that handle kind of going straight up and out. It does say in our problem statement that the end of the handle is a point of interest. So I do want to go all the way out there, and I have a pin connection right about here. Now, sometimes you're like, can I just leave it like that? You could. But as we look at this kind of in terms of when we look at that piece, it kind of looks like it's two separate pieces because of that joint in the middle, doesn't it? It looks like it could be two separate pieces. So to make it more obvious that it's a single piece or a single link, what I'm going to do is I'm just going to add and use that triangle method to add a little bit of thickness to this so that you can see that that is a piece that's, all together. Does that make sense? Do you kind of see how that kind of helps us a little bit? But if you would leave it as a straight line, I don't think it would be wrong, but this would be more clear. All right. Then the next one is going to be this connecting rod that is going to go to my slider. Okay. So my connecting rod, now we don't have dimensions. So again, proportional drawings would be good. So that's going to be, I'm going to call it my connecting rod or coupler, sometimes referred to as. And then at that center, this is where we're going to draw that rectangle. And then we have it vertically constrained. Okay. vertically constrained. And that's it. As far as what it looks like. Now we got to add our labels. Our first label, actually, before I do my labels, does anybody have any questions as we look at this? Okay. Even if you didn't get it the first time, like by yourself, that's okay. That's why we're practicing this, giving you some looks at it, and then you'll start to be able to apply, you know, to other kinematic diagrams. So number one is going to be my frame. Again, I like to start at that, and I like to then go and where is my input? My input is going to be this handle, so I'm going to call that number 2. I've got that coupler or connecting rod, that's going to be number 3. And then my output is going to be that crushing mechanism going up and down. So that's going to be 4. Then I need to identify my joints. So any primary joints, which are pins in this case, I've got 1, 2, 3 pins. So that's going to be an A, a B, and I'm going to sneak C in right there, like right by where it connects to the slider. But there is one more joint, which is also a primary joint. Does anybody remember my last joint, Ben? Yes, it's the slider. So some way, somehow, that is going to be constrained to only be able to go in a linear fashion. So we call, and you can do it on either side. We call that you know, 2 surfaces coming together, the slider and, like Ben referred to it as the wall or the surface that it's riding on, is going to be another primary joint, but it's a sliding joint instead of a pin. Okay. All right. So that's our kinematic diagram. Let's go ahead and create this in AutoCAD. Okay. So I'm going to go back over here. I'm going to save my 1.3. I'm going to open my kinematic start file again. And then I'm going to rename this one, save as, and this one is going to be example 1.4. Now, yesterday somebody asked, can I put all of my diagrams in one file? Yeah, you could, because you're really going to be taking the screenshots, but then just make sure that you label them separately so that you know which ones are which, and you could put them all in one file. So you could call this file, if you wanted to, practice problems 1A or something like that. Okay. But I'm just gonna do them as separate files because I don't know, that's what I'm gonna do. And I'm gonna turn off my ortho. I'm gonna bring this down. Okay, so this is going to represent my frame element. Now I'm going to add the center here, my handle. Oops, I gotta change my layer. And go back. And then I'm going to copy my pin connection. And I'm going to put this along there. So nearest here is good. Then I'm going to move my slider over because this one, I can utilize this, right? And then what I'm going to do is I have to rotate it 90 degrees. There we go, because it's going to be vertical. And I'm just going to move it over a little bit. I don't know exactly where it's at, because again, we don't have dimensions, so we're just going to represent proportionally. And now I'm going to go from center here to center here. Okay. Now, sometimes students are like, how do I connect this L here? Remember, we're not representing, we're not showing the details of how these elements are connected. So for instance, sometimes students get a little bit hung up on, well, this slider is on the same thing as where that's connecting. Don't worry about that. All right. Those are details that you figure out in the individual part design. Okay. We are at the layout mode. So we just know when we look at AutoCAD here, we just know that that's going to be going up and down. You know, I don't know exactly what that's going to look like, how it's going to be configured yet. That's a little bit down the road. Okay. So we're just practicing creating the kinematic diagram for something that looks and acts like a can crusher. Okay. So any questions on what we see here? All right. Then I'm going to add my labels. So I'm going to move over. Oopsie. Number 1. I'm going to move over number 2. I'm going to call my handle number 2. That connecting rod or coupler is going to be number 3. And number 4, just as I did in my example, is going to be my slider. Okay. It's a little bit closer, so I'm not so far away. Oops. Now I'm going to move A there. I'm going to move B to the next primary joint. C. Oops. C. I don't know if I'm going to sneak it in there or not. So I'm just going to put it above, and then I'm going to move D. I'm going to put it nice and close to where the slider hits the surface. And then I'm going to move X to the end of my handle because it said they wanted the handle to be a point of interest. So the things that I didn't use, these guys. Okay. So there we go. Any questions about using AutoCAD to make the diagrams? This is going to be what you're going to screenshot. Make sure that you label it. So in this case, this is sample 1.4. And I did it again. Put it on the notes layer. There we go. And now you can take your screenshot and add it to the document where you have the previous 2 examples. Okay. That's the first part of example 1.4. The second part is the mobility equations. So let's go back underneath our camera and we will add the mobility equation underneath 1.4 here. So the mobility equation is going to be F is equal to 3 times n minus 1 minus 2 JP, not JB, JP. Okay. So knowing that n is the number of links and JP is the number of primary joints, our numbers are going to be 3 times 4 minus 1 minus 2 times 4. If you forget to put D in here, which it is easy to forget it because that's not a, you know, a pin joint and we're not like making a special symbol for it, but because it is constrained vertically in this case, linearly, there is a joint there that keeps it from, you know, not going in any other direction, but vertical in this case. So there is a primary joint there. If you forget that, this is going to be 2 times 3, and you're going to get 9 minus 6. Okay. And you're going to have 3 degrees of freedom. And you're going to wonder, well, what 3 things do I have to do to get this can crusher going? There's only one thing I have to do, and that's going to be the handle. So knowing the operation, you should get the number that you're expecting. So that's why we use the degrees of freedom equation to make sure that we have everything set up correctly above. So my F is going to be 9 minus 8. So my F is going to be 1. So put a box around that to let me know. And then this would be another thing that you would, again, make sure I understand that this is the mobility equation for example 1.4. And that's going to be what you have to hand in along with the screenshot of the AutoCAD work that you did. All right. Any questions so far? Okay. All right. Then what we're going to do is I'm going to go back to our PowerPoint presentation. And we are going to go to our next section. So the section we were just working on was 1.7. Now we're going to skip over to 1.10. And that is going to be found on, it looks like on page 19. And And so you'll notice here that we skipped a couple sections and a couple pages. So, so this is where I want to just reiterate that you are only responsible for the pages and the sections that I go over during our lecture and are found in our PowerPoint. If there's anything in between there, you don't need to worry about it, okay? So I'm just I pull out the stuff that we focus on that's gonna be most important for you to know and that you're expected to do for your homework. So we're gonna look now at a 4-bar mechanism. So a 4-bar mechanism is the simplest and most common of all the mechanisms that are out there. So 4-bar mechanisms are applied in a lot of different ways, and we're going to see that throughout this course. Okay, so predominantly the number of links that we're going to see in the mechanisms that we analyze is going to be 4, and that's why it's called a 4-bar mechanism. So number 1 is always going to be the frame, as we've been practicing. And if it is a true 4-bar mechanism, then we usually have, and I've alluded to this already as well and used this terminology, we're going to have an input link, okay? So it could be a crank where it goes around in a full circle, and that's going to be our number 2. Our third link then in a 4-bar mechanism is going to be the coupler or connecting rod, sometimes referred to, and that's going to be number 3. And then our last one is going to be whatever the output is, and that's going to be number 4. So traditionally, that's how we number, okay? If you, anything but 1, okay, anything but 1, you can put in different orders, okay? But you're going to see that I'm going to practice it like this, and in the book, most often, we're going to see this in this format as well. Now, there are different types of 4-bar mechanisms. The 3 common types are going to be crank rocker, double crank, and double rocker. And we can see those on the top of page 20. So if we go to the top of page 20, we've got examples of each one here. So I'm going to zoom in on that illustration. Okay. Now, as we look here, we're going to look at the top one here. This is called a double crank. A double crank, whenever we refer to as the motion of an element in a mechanism and refer to it as a crank, that means it's going around 360 degrees. So if I've got a motor connected to something, it's going around, that's a crank. It's going to be going around 360 degrees. If I have, you know, maybe a manual crank of some sort, and I can move it all the way around a full circle, that's going to be considered a crank. So on this mechanism right here, we've got 2 cranks, meaning that each one of our input and our output are going to go around a full circle. Okay, so crank just refers to the motion of that link, right? The next one that we see here is a crank rocker. A crank rocker means that our input crank is going to go around a full circle, but the output is going to oscillate back and forth through, you know, a certain amount of degrees. Okay, so this means that they're not both going to go around in a full circle. Again, one is going to go around in a first circle. That's going to be the input, the crank, and then the output is going to oscillate instead. Okay. The next one in the middle here, this is a double rocker. Okay, a double rocker just means that neither one of them is going to go a full circle around. So the input is going to be a rocker and the output is going to be a rocker. Our diagram here that we did, for example, 1-3, that was a toggle clamp. So our handle is only going to oscillate. It's not going to go around in a full circle. So that is not a crank. This is going to be a rocker. Okay. And the same thing with the output, which would be the clamping portion. This is going to oscillate, not go around in a first full circle. So this is a rocker mechanism. Okay. The one down here, this is another example of a crank, but it's called a change position because the connecting rods, if you would, are going to be the same size. So you get you just get a difference of a distance between the 2 motions, but they're the same or a mirror image of each other. And then the last one we have here is called a triple rocker. And the triple rocker just means that the input is rocking, the output is rocking, and so is the connecting rod. So it's got a specific type. So so those are the main, you know, kind of types of 4-bar mechanisms. The last type that we're going to talk about, And I'm going to actually skip ahead a little bit on our, and we're going to come back to this example. The other kind of 4-bar mechanism that is very popular, and we're going to see this quite often, is going to be the slider crank mechanism. And that is going to be like the can crusher that we just did. So in this case, we had our handle and we've got a slider, okay? In the example that we see here, we've got, again, oopsie, I have to do my zoom. Here we have the input, which is going to go around in a circle, crank. It has a connecting rod, and here we have a blade that is going to slice or cut something, and that is going to be constrained to be vertical. So this is going to be our slider. So a crank, slider, or a slider crank, you can say it in either order, is going to be the type of mechanism that this is. And again, it's going to have 4 elements to it. It's a configuration of a 4-bar mechanism, but it doesn't have the last link oscillating or going around in a circle or pivoting around a center. So let's go back. We have 2 more examples, I believe, that we're going to be, oh no, I guess one more example that we're going to be looking at, that we're going to be handing in for our practice problems. And this is going to be example 1.9. Now, example 1.9, actually, the problem statement is at the very bottom of page 20. Okay, right here is the problem statement, but the illustration is up here. So I'm going to zoom in on this. All right, and it says here that we have a nose wheel assembly for a small aircraft is shown in this figure right here. Classify the motion of the 4-bar mechanism based on the configuration of the links. Okay, so first things first, just like we did on the last 2 examples, what I want you to do is I want you to sketch what you believe this mechanism should look like in kinematic form. If you want to peek down a little bit lower on the page here, they do have their version of it, but I want you to take time to sketch it here before we translate it over to CAD. And go ahead and number and letter your joints and your links. And hopefully by doing these couple of extra examples, it really kind of helps to kind of get the process going, because as you do your assignment, you're going to have some other looks and other types of mechanisms that you're going to be doing. So, so the whole point of this is to prepare you for those. Okay, and then the ways that you're handing in are going to also be the same formatting that I'm expecting for any homework problems in that assignment that you're going to be doing. All right. So if you do peek down below, totally fine, but you should get something that looks like this. All right. Now, probably the biggest difference here is that if we look at my link number 4, it doesn't look like a wheel at all. But remember, when we're doing kinematic diagrams, they are not supposed to look much at all like the actual mechanism itself. Those are the details that we add in as we, finish up the design. Okay. And that's not the intent here. This is layout. So we just want to show the extents of and what the important points would be. Okay. So I think it did say that it wanted, or did it tell us? Didn't necessarily, but not a bad idea to add the point of interest out here. This just represents kind of as we would go straight across the very bottom of that wheel. So we know, how far it's going to go. Now, a couple of things here before we go further. Number one, as you're looking at this design, what type of a 4-bar mechanism is this? Is it a slider crank? Do we have a slider here at all in the kinematic diagram? No, it's not a slider crank. So we can take that one out. But we had rocker, rocker. We had crank, rocker. We had crank, crank. Is this one any of those, do you think? Go ahead. You think it's rocker, rocker? Okay. So as we look here, we've got, looks like it might be a motor out here, right? And so you're going to notice that it would rotate around here, right? And then this is probably going to go back and forth, right? Not a full circle for sure. Now it's hard to say if this is going to go around a full circle or if it's going to go around just, a portion, if it's just going to reverse and go back the opposite direction. Not really exactly sure. So either calling it a crank rocker without that extra information or a rocker rocker, I think that would be fair to assume. Now, that's not part of what you need to hand in. The next part that we need to hand in is going to be our mobility equation. I'm going to choose for this last example, just for time efficiency. I'm not going to do the AutoCAD, but you will before you hand it in. Okay, so when you hand in example 1.9, you need to do the CAD. Okay, I'm confident that you can, but that's going to be part of your practice problems. Just in the interest of time, I'm confident that with your experience and with the ones that we went over, that you have a good idea of how to do the CAD. Now what we're going to do is we're going to add the mobility, and we're going to first predict, what do we feel our mobility should be? How many things have to happen in order to get that wheel to oscillate the way we need it to? How many inputs do we have to do? Go ahead. Just one, right? We just have to turn that motor on, and that motor is going to be the one thing that is going to operate in order to get that wheel to oscillate back and forth. So our hope is that our F comes out to be 1. Okay. So let's see. So we have F is equal to 3 times N minus 1 minus 2 times JP. So I'm repeating this again. You have to write the equation out for each and every one of these. Yes, for each and every one. And then what you're going to do is you are going to add in the numbers. So 3 times the number of links. I've got 4 links identified. 1 frame, 2, 3, and 4. So it's going to be 4 minus 1 minus 2 times the number of primary joints. So I count up however many letters I have here, and there's 4. So if I do my math here, this is going to be 9 minus 8. That's going to be 1. Okay. When you do your homework, not all of them are 1. All right. So you get to look forward to seeing which ones are different. All right. So again, you will be adding the CAD for this one. Okay, we demonstrated the other ones. Unless anybody wants to see it. Does anybody have any questions yet on how to represent this in AutoCAD, or you feel good about it? Make sure that you do that. You'll be adding that, and then also your mobility equation here. Okay. So that's example 1.9. We talked about the slider crank mechanisms. Now, techniques for mechanism analysis. So things that you need to know in order to create kinematic diagrams. So when we create them in CAD, and as I told you, CAD is required for the practice problems, all the practice problem examples and the homework problems, okay? You really just need to know the things that we already looked at. You need to know how to, put lines down, circles, trim, extend. Hatching is something that we did. And then also, changing your layers, putting in text where appropriate, okay? I want to emphasize that whatever colors you choose, you don't have to use the same colors that I was using. I use them so that I can see them and that you guys can see them. If you choose to use darker colors or lighter colors with light backgrounds or dark colors with dark backgrounds, and if I can't look at it and efficiently see it, I'm not going to try to squint and figure it out. It's just a 0. All right. You're not going to get the points for that. So keep that in mind when you're handing in the files. Again, how would you present this to somebody when you're working out in industry so that they could understand what you did? Okay. So make sure that that's there. Also, you're going to notice that in the assignment and in the things that we didn't have any dimensions in this first part of module 1. Just proportionally make sure that the diagrams look appropriate. Okay. And I think that's the end. So that means that we're ready to start looking at our assignment. I'm going to stop our recording here and we'll take a break. And then when we come back from our break, we'll take a look at all those homework problems and I'll start a different recording as an overview for the assignment so we know what we're doing for that. So I am going to